Good morning and welcome once again to your topology class. In the previous classes, you have done the topics of T0 spaces, that means Kolmogorov spaces, T1, that means Frechet spaces, and something about the Hausdorff spaces, T2 spaces. Now we will proceed further on to the T2 spaces. So we will move on to the first theorem today. The first theorem today is the property of being a T2 space is preserved by 1 onto open maps. That means you can also say that property of being a T2 space is a topological property, because we know that if a property is maintained, is contained by, or is preserved by a 1 onto and open map, then it is called a topological property. So property of being a T2 space is also a topological property. So how to prove this theorem? So now I will move on to the theorem's proof. So how to prove it? First we will write whatever is given to us. We are given that let X tau be a T2 space and let F be a map from X tau to another topological space, that means Y rho, and this is given to be 1 onto and open map. What we are to prove that? We are to prove that this Y rho is also a T2 space. That we are to prove. So first I will write what to prove. So to prove is that Y rho is also a T2 space. This we are to prove. And now we will move on to the proof. How to prove it? So to prove that it is a T2 space, we will have to take two distinct points from Y, and we will have to find two open maps containing one of the points such that their intersection is phi. So let us start. Let Y1 not equal to Y2 be 2 points of Y, and now we have to show that there exist two open sets containing Y1 and Y2 separately, and the two open sets are disjoint. The intersection of these two sets is phi. Since Y1 and Y2 are points of Y and the map F is onto, so Y1 and Y2 must have pre-images in X. So therefore there exists X1 not equal to X2. Why I am writing here not X2, not equal to X2? Because the map is not only onto, it is also 1. So distinct elements will have distinct images, and distinct elements of Y will have distinct pre-images. So if Y1 is not equal to Y2, then X1 will not be equal to X2, such that f of X1 is equal to Y1 and f of X2 is equal to Y2. So this is now, we are having now 2 points X1 and X2 in X, but X tau is given to be a T2 space. So now X1 is not equal to X2, belongs to X, and X tau is T2 space. So therefore there exist G and H belonging to tau such that X belongs to G, Y belongs to H, and intersection of G and H is phi. This is because X tau is given to be T2. Now, your X is in G. I must write here x1 and x2 instead of x and y, because the 2 points I have taken are x1 and x2. So x1 is in G, x2 is in H. Since x1 is in G, therefore f of x1 must be in f of G. And similarly, f of x2 must be a member of f of H. I name this fg as G1 and I name this fh as H1. Now these G1 and H1 are both open sets. Why? Because G and H are open and F is an open map. F is an open map, so f of G will be open, that means G1 is open, and f of H is open, that means H1 is open. On the other hand, this f of x1, this is y1, and this f of x2, this is y2. So I can say, therefore I can say there exists G1 H1 belonging to. Now G was open in top and topology of X was top, but f of G will go into the image set Y and the topology there is row, so this G1 is open, so it must be a member of row. Similarly, H1 must also be a member of row, so there exists G1 and H1 in row, the topology of Y, such that your Y1 belongs to G1, comma, your Y2 belongs to H1, Y2 belongs to H1, and now think of intersection of G1 and H1, and G1 intersection H1. What is your G1? G1 is f of G and H1 is f of H. So f of G intersection f of H, you can also write it as f of G intersection H. But what is G intersection H? G intersection H is phi. So it is f of phi, and we know it very well that f of phi is phi. So what we have proved, we have taken two distinct points y1 and y2 from Y, and we have obtained two open sets G1 and H1 in the topology of Y, that means row, such that y1 belongs to one of the open sets, y2 belongs to the other, and the intersection of these two open sets G1 and H1 is phi. And this all proves that the topological space Y row is a T2 space, what was required to be proved. So what we have proved? We have proved that Y row is a T2 space, and that was required to be proved in this theorem. So this proves that the property of being a T2 space is a topological property. Now the two basic properties in topology are, one of them is topological property, which we have just proved, and the other one is hereditary property. So next will be the theorem based on hereditary property. Theorem. This is the theorem. So let X top be a T2 space and let Y be a subset of X. Obviously Y is not phi. Then show that Y tau Y. Tau Y, you know what it is. It is the relative topology defined on Y. I'll write it in the next line. Then show that Y tau Y is also T2 space, where what is tau Y? Here tau Y will contain the sets of the type G intersection Y, where G is a member of tau. That means what you have to do, you have to take all the members of the set tau and then intersect them with the set with the set Y, and the sets G intersection Y will be the members of tau y, and this will become a topology. We have proved already in the previous chapter, and we have to show that this y tau y is a T2 space. That means we have to show that if a topological space is T2, then its subspace, then its relative subspace is also a T2 space. That means the property of being a T2 space, or you can say the Hausdorffness, is hereditary property. So that what we are going to prove now. So I am going to start the proof now. We are given that X tau is T2 space. This is given to us. And what we are to prove? To prove y tau y is also T2 space. This we want to prove. To prove this, what we are to do? We will take two elements from y and we will find two tau y open sets containing each of them such that their intersection is phi. That means the sets, open sets, are disjoint. So we'll start from here. Let x and y be two distinct elements of the set y. Now what we are to prove? We are to find two open sets, tau y open sets, one containing x, other containing x, and the two open sets must be disjoint, and that will make that the topological space y tau y is a T2 space. Now x and y are distinct elements of y, but y is a subset of x. So this means x and y are distinct elements of x also. But what about x? X tau is given to be T2. Since x tau is given to be T2 and x and y are two distinct elements of x, therefore by definition of T2 space, there must exist open sets G and H such that x is contained in G, y is contained in H, and G intersection H is phi. This is now given to us, but these G and H are tau open sets. These are not tau y open sets. We have to find two tau y open sets. So we'll move on to obtain two tau y open sets, one containing x, other containing y, and the two tau y open sets must be disjoint. So what we have to do? This x is in G, this x is also in y, x is in G, x is in y. That means x belongs to G intersection y. Similarly, y is in H, y is also in y. So y must be there in H intersection y. Rename these two as G1 and H1. Now look at, your G is tau open. Your G is tau open, and every tau open set when intersected with y will become tau y open set. So this G1 will become your tau y open set. Similarly, your H is tau open set, and this H tau open set intersected with y will become tau y open set. So that means you can say there exist tau y open sets G1 and H1 such that x is contained in G1, y is contained in H1, and the third property, that means G1 and H1 must be disjoint. That means their intersection must be phi. Let us see, is it or not? So G1 intersection H1. What is your G1? G1 is G intersection y. Okay, this is G intersection y, and intersected with H1. Your H1 is H intersection y. Now everywhere here you are having the sign of intersection. So you can write it together. You can write it in the form G intersection H intersection y. But what is your G intersection H? Your G intersection H is phi. So this is phi intersection y means phi. So what you have obtained? You have obtained two tau y open sets G1 and H1 such that X is in G1, Y is in H1 and their intersection is phi. And what are these two X and Y? These are two arbitrarily taken distinct elements of the set Y. And this all makes that your Y along with the topology tau Y is a T2 space. So what you have proved finally, this means your Y tau Y is a T2 space, and that was what required to be proved. So this is the second theorem. First was the theorem in which we have proved that the property of being a T2 space is a topological property, and now we have proved that the property of being a T2 space is also a hereditary property. That means the relative subspace of a T2 space is also a T2 space. And now we move on to the next theorem. So next theorem is in a T2 space, singleton sets are closed. Singleton sets are closed. Okay, so we will prove it now. Let X be a singleton set in capital X. That means this X is an element of X. Take Y not equal to X, also belonging to X. One element I have taken this as X, the other one is a distinct element from X, that is Y, and both these X and Y are the members of X. But this X is a T2 space given. So what will be there as a result? There must be two open sets containing X and Y which must be disjoint. So you can say, I'll take one of them only. So let there exist tau open sets GH such that X belongs to G, Y belongs to H, and G intersection H is phi. Now look that. G intersection H is phi. X is a member of G, which means singleton set X is a subset of G. Because X is an element of G, the singleton set X is a subset of G. Now, H has a empty intersection with the set G. If H is having empty intersection with G, that means H has empty intersection with every subset of G, and singleton set X is also a subset of G. So this means singleton set X intersection with H is also phi. But what is H? H is an open set containing Y. So you can say that H is a neighborhood of Y. So there is a neighborhood of Y which intersected with the singleton set X gives you the empty set. That means Y cannot be a limit point of the singleton set X. So this means Y cannot be a limit point of singleton set X. But what was Y? Y was an arbitrary element which was not equal to X. That means other than X, no element is a limit point of X. And that proves that the derived set of the singleton set X is phi, because no element other than X will be now a limit point of the set X. Note that closure of a set is the set along with its derived set. But the derived set of X is not phi, so it is singleton set X union with phi. That means singleton set X. So closure of singleton set is same as the singleton set, which makes that the singleton set X is closed. So this means singleton set X is a closed set, and that was what we needed to prove, that every singleton set is closed. So since X is an arbitrary element and we have proved that the singleton set X is closed, that means every singleton set is closed. So here I am going to stop this video. In the next video we will have more and more theorems on Hausdorffness. Till then, wait for the next video. Thank you once again.